Hey everybody, yesterday's lecture was very content heavy, and as a result I did extend the deadline for the homework to Sunday, from Friday to Sunday. I don't want you to take that as an opportunity to start the homework later. I think you need the extra time, so please start it when you normally would and reach out with any questions. I'm happy to address those as always. Today's lecture is going to be significantly lighter than yesterday. We're just going to go over an example applying a lot of the content that we covered yesterday. So in this example, we're looking at the relationship between pulse rate and exercise. Specifically, we want to test if people who exercise regularly have a lower pulse rate than people who don't. And you could look at the definitions of how regular exercise is defined, listed in the second bullet. The first thing I want you to think about, besides how the hypothesis is defined, is whether this falls into a one sample, two sample, or paired sample t-test. Okay, so hopefully you came up with the right hypotheses. This is a one-sided test, and it's pretty arbitrary what subscript you use to denote the different means. You should use mu as opposed to x bar because we're talking about the population. I went with n to define the mean of the people who are not actively exercising, and a for the mean of the group that is actively exercising. And I was explicit in including the less than. You could have written just an equal sign here, but it is implied that the non-active group could have lower or equal to pulse rates to the active group as your null hypothesis. Whereas your alternative is one-sided, you want to see if the active exercisers have a lower pulse rate than the non-active exercisers. And as far as whether or not this is a one sample or two sample t-test, it's obviously not one sample because we have two groups that we're comparing the means of. You could argue it's a paired sample, but there's really no natural pairing here. Like, how do you decide who from group 1 you're going to take the difference of from group 2? Like, you could do participant 1 versus participant 11, participant 2 versus participant 12, but that's a pretty arbitrary distinction. There's no natural pairing. It's not like we took the same participant and took their pulse rate before exercise and after exercise, right? And these are just 10 random people in either group. So by far, the more appropriate answer is a two sample t-test because we're comparing two means of two groups. So let's go ahead and do that. I'm going to open up Excel. I know this formula is a little intimidating. Before we get into it, notice that mu A minus mu B in our case is 0. So we can ignore this part of the formula, and that makes it a lot less intimidating. So let's go ahead. I'm going to copy this into Excel just as a point of reference. So here's some data that I made up about people who exercise and people who don't. And the first step, as you can see in the numerator, is to calculate the difference in means. That's pretty easy in Excel. It's just the average function. Right? We have the mean of people who exercise compared to the mean of people who don't. And this is a good sanity check in interpreting if your results are accurate or not. We see that people who exercise, at least in this data set, have a lower pulse rate, right? You're looking at 70 and change versus 87. On average, they have a lower pulse rate. So we expect our p-value to certainly be less than 50%, which would be the point at which they're equal. It depends on whether it's one-sided or two-sided, but knowing that the sanity check, let me reword that, is that we expect like a relatively low p-value because, and let me remove these decimal places, because we see that the mean, and let me label it, is indeed lower for people who exercise, which is our alternative hypothesis. So it would be really strange if we got a p-value of like 0.9. This is just a quick sanity check we expect a relatively low p-value just based on what we're seeing in the means. However, that's just the numerator, right? It also, we have to account for the variation. So let's go ahead and calculate that. We already know NA and NB are just 10 because the two groups are the same size. So let's go ahead and calculate the standard deviation, or actually this is the variance because it's the standard deviation squared. So let's calculate that instead. And I know we had been calculating it by hand and that was good practice, but at this point I think you can use the formula VAR. And notice there's var p, which calculates variance for the population, and var s, which calculates it for the sample. In this case, we're obviously dealing with a sample, so we want to use var.s. So let's calculate the variance of these two. Notice I'm not including the mean in that calculation, just the raw data. Oops, sorry. Okay, so I've done that, and now I could calculate my t-statistic, and I'll do that over here. I'll label it as t, and that's going to be equal to, so group A minus group B. Is that the way I want to do it? No, I'm going to do it the other way. You could do it as A minus B. The reason I'm doing it the other way is it's going to give me a positive numerator, which might be a little trickier to interpret because I want the right side of that tail. But if you look at our hypothesis here, the way we defined it was one-sided. It is right-sided. Again, there's no right answer here. You could do it in either direction. Just make sure you choose the appropriate side when you take your t-statistic and convert it into a p-value, which we'll go over how to do in more detail for the first time shortly. And you know what? Let's just do it both ways. It's good practice. So I'm going to start by taking the difference, and I'm starting with this by taking the difference of the exercise group of the no exercise group from the exercise group, but we're going to do this both ways. And then I'm dividing by the square root of the variance over 10 plus the second group's variance over 10. Right, and I could wrap that in parentheses too if I want to be extra safe. Hold on. Forgot a parentheses in my formula, that's why I was complaining. Okay, and this gives me one t-statistic. Now, when I do it the other way, this is another good sanity check. I should get the same t-statistic, because remember the t-distribution, the standardized t-distribution is symmetrical around 0. So this is a good sanity check. So this time I'm taking the mean of the no exercise group, or the mean of the exercise group, and subtracting that from the mean of the no exercise group. I keep forgetting my parentheses, and Excel does not like that. Okay, so there's my numerator, and I'm going to divide by the same exact thing, square root. This time I won't include the extra parentheses, they're not necessary. So because of according to the order of operations, you're going to do division before addition, though it does vary based on the tool you're using. In this case, I think we're okay. Okay, so here we go. And I get the same exact answer. It's more obvious if I remove some decimal places. It's just positive now. So that's what we expected to see. Now the question goes, how do I convert this t-statistic into a p-value? Now I want to know the area under the t-distribution for this value or more extreme values. And there is a handy function in Excel to do this. There's a handy function in every piece of statistical software to do this, or you could use tables, but nobody really does that anymore. They just use statistical software. And the function here, you could type in t if you're unsure, and you see there's a lot of choices here. So t-distribution, if you mouse over it, it'll give you a little description, is going to give us the area to the left. Whereas t-distribution RT for right-tailed is going to give us the area to the right, and then 2t is the two-tailed test. In this case, because this is negative, I want the area to the left. Although we'll check it and show that when I do this t-statistic and the area to the right, I get the same p-value, just as a quick sanity check. So let's go ahead and do t-distribution. It's going to ask me for my t-statistic, which is right here. Then my degrees of freedom. And this is actually a little tricky here, the degrees of freedom, because there's two sample sizes of 10. So a common mistake is people will say, well, it's 9. But if you flip back to our slides, you'll notice the formula for the degrees of freedom is actually pretty complicated. It's this long formula. So let's go ahead and use that formula. I'm going to copy it into Excel for a point of reference. Well, for now, I'm just going to put 9, or I guess a more accurate estimate, it should be like around 18. And I do want it to be cumulative. I think that's the default argument. And we get a p-value of like 3%, but that's not the correct degrees of freedom. So let's go ahead and copy this formula for reference into Excel. Okay, let's calculate the proper degrees of freedom. So the degrees of freedom should be equal to the variance over the sample size, which is 10 for both of them, plus the variance over the sample size. That quantity squared is my numerator. And then I'm going to divide by, I know this is a little confusing. You have the standard deviation to the fourth, but that's the same thing as the variance squared. So you don't have to be as intimidated by it. So that's going to be divided by the variance squared over, now here I have my sample size squared, which I know is 100, but I'll just go ahead and write it out, times my degrees of freedom in group 1. That's what that V, it's really the Greek letter nu, is representing, the degrees of freedom. And we know that to be 9. So it doesn't hurt to put extra parentheses if you're not sure if the order of operations is being applied correctly. But yeah, so that's the first one. And then the second one's going to look very similar, right? It's going to be, again, my variance to the fourth, or squared, my variance squared, standard deviation to the fourth, divided by, again, 10 to the 2 times my degrees of freedom for the second group is exactly the same. And just to be safe, I'm going to put an extra parentheses here because I don't want that order to potentially get messed up. And I think we're good. I'm going to put an extra parentheses here just to be on the safe side. Make sure the order of operations is followed correctly. I forgot a parentheses anyway. And I can see these degrees of freedom is wrong, so something's wrong in my formula, right? I shouldn't get a degrees of freedom of 2 when I have two groups that are of size 10 each. So let's see what's going on here. Variance squared divided by 10 squared times the degrees of freedom plus variance squared. That all looks right. So I wonder if the issue is in the numerator. Let's try wrapping this in parentheses, see if it still complains. Let's try breaking this up into pieces and see where we made a mistake. Okay, so for the numerator, I do variance divided by 10 plus variance divided by 10 and square that quantity. So that's my numerator for degrees of freedom. And then for my denominator, I'm taking variance squared divided by sample size squared times degrees of freedom. That all looks right, but let's break it into more pieces just to be safe. Okay, so here I get 129, and then here I get, and I'm seeing this is going to be about 1.8 because this is going to be 129 too. I guess it, oops, this appears to be where the mistake is going wrong. So it is 10 squared times 9, and it is variance squared, but why is this? It says they should be roughly the same because the variances are roughly the same, so something B11. Oh, and that's the issue. I selected the mean instead of the variance. So I needed, and some of you may have caught that, but yeah, I needed the variance here. Okay, so This is going to give me a lower degrees of freedom now because I squared that quantity. Variance of 1 divided by the sample size plus variance of 2 divided by the sample size, that quantity squared is my numerator. That's correct. I wonder if I made a similar mistake here. Is that variance squared divided by sample size squared times degrees of freedom? I wonder if I chose the mean here. Oh, yeah, I did. I chose the mean instead of the variance, so that's my issue. Even though I labeled them, I still chose the wrong values. And there's an alternative way to write this formula that I think is a little more intuitive, but we won't get into that right now. So here we divide that by this plus this. And this is a much more reasonable estimate of degrees of freedom. I expected it was going to be around 18. And the reason I did it, I knew it was going to be around 18, is we didn't talk about pooled variance. But pooled variance, like here we're assuming there's an unequal variance between each group, the non-exercise group and the exercise group. In pooled variance, you assume that it's the same variance and any differences is just due to random variation in your sample. And the formula for degrees of freedom of pooled variance, which is very close to this more complicated formula for the degrees of freedom when you have unequal variance, is just NA plus NB minus 2. And I did, in fact, get a degrees of freedom that was very close. So let me go ahead and plug that into my distribution instead of 18. It's not going to change a lot because it's pretty much 18. And I get a p-value of, let's make it a percent so it's easier to read. Throw some decimals on there. 3.46. And I should get the same thing if I do the t-distribution function here. Just note I need to do right-tailed because I want more extreme than 1.94, which would be to the right. Oops, I didn't put the argument in there. Here's my t-statistic. Here's my degrees of freedom. And it's not even asking me if I want it to be cumulative or not because I specified that it's right-tailed. But I think by default it assumes that argument is true. And I do get the same value as before. So yeah, we get a p-value of 3.46. So are these different? Well, if I use the traditional alpha of 5% or 0.05, you would conclude, you would reject the null hypothesis that there's no difference in pulse rate between the exercise group and the no exercise group, and conclude that there is in fact a difference. So yeah, hopefully that was helpful to you. You're going to do a very similar question on your homework for this week, and looking forward to seeing how you guys do on that. See you tomorrow.